Hello, everyone. My name is Derek Wojciak, and I'm joined by my colleague Luc-André Grégoire. And today we're going to have another episode of the OPAL-RT learning journey. The topic for today is challenges and limitations of real-time simulation that are raised by high switching frequency power converters. So I know it's a long title, but stay tuned and you're going to see what we're talking about here. So in terms of the outline for the webinar, I'll start off with a very quick introduction, introduce a little bit of the subject, and then Luc is going to go in full detail with various converters. So he's going to start off with a buck boost converter, then a dual active bridge, and then finish off with an LLC resonant converter. And then we'll have about 5 minutes at the end of the presentation for any questions you may have. So at that point, I do recommend inside the go-to platform, there is a question tab that you can click. And throughout the presentation, feel free to ask any questions and we'll get back to them at the end of the presentation. And if we don't, we'll always send you a follow-up email on that. So let's get started. So I think just to set some context, I think we should talk about the reality of simulating these high switching frequency topologies. So if we were to talk about this, just a few years ago, it wouldn't be possible. So throughout the past couple of years, we've worked with a lot of our users to be able to optimize our solvers and our software to be able to support these very high switching frequencies. So when I'm talking about high switching frequencies, I'm talking in the range of hundreds of kilohertz. Like I said, we weren't able to do this many years ago, so now we're finally at the point where we can simulate these in real time and allow the users to test their controller. I also want to highlight that the focus for today's webinar is sort of on the onboard charger inside of an EV. The reason for that is because obviously, the higher the switching frequency, the smaller the components inside of the onboard charger, the less heavy it is, and that kind of equates to more range inside of a vehicle. So that's kind of been the pioneer for us. We've worked with a lot of our EV customers to push in that direction and get them to increase the range. But we can see that what we're doing here is applicable in all industries. So if you are coming from an industry that isn't part of transportation, don't worry, because we see that this is prevalent in all industries. So next, I'll let Luc kind of go ahead and introduce the subject and go through some examples.
All right, so hi everyone. So I'm more used to a live audience, but my first thing would be for you to think about how many reasons there is to use a real-time simulation. So I'll give you a second and then, yep. So if you think that there's more than one, there's actually only one reason to do real-time simulation, is to actually connect real hardware to a simulated model. Now, how many purpose for a real-time simulator? So you just spent a lot of money for that, so you might want to make it more useful than just one single thing. So there's mainly three reasons. So you can go for rapid controller prototyping, what we call hardware in the loop, or non-real-time simulation. So to go fast through all the different process, so if you go for non-real-time simulation or pure simulation, you have one simulator here, and then you can simulate both the controller and the plant, and everything happened within the simulator. So if you have a very large model, the idea might be to go faster for the simulation rather than just using your computer. If it can go slower than real time or faster than real time, then the next step that you might go through is just add some IO. So the controller and the plant are still in the simulator, but then you just connect IO to loop back from the simulator to the simulator. So the model and the controller only talk through the IO. At this point, you really need to be in real-time simulation because you have physical IO connected. After that, what we have RCP is then when you use the simulator to design your controller so that it can help you to know exactly what the time step you can achieve and how much computation burden you'll have to implement on a smaller controller, and then it's connected to a plan. So that's what's called RCP. Then we have hardware in the loop. So you have your controller, and before putting it into the real world, you're gonna test it against the simulator that is in the plan. And then you can go one step further with what we call power hardware in the loop, in which case your controller is interfaced with a real converter or whatever purpose you want to use it for, but that has actual higher power. So you have a plan that is connected to an amplifier, and then the model of that you want to simulate is control the power amplifier and so on. Now, the difficulty in real-time simulation is that this is the purpose, like the chart for every time step. So every time that you do one computation time step, you first read the input, compute the model, and then you exit the output to go out of the simulator. So from the data acquisition to the generating the signal through the analog out or to the digital output, that's the way that it has to be done, and everything has to be done within one time step. So depending of the time constant of your circuit, you have more or less time, and depending of the computation burden that you need to do, so sometimes it might be like that, at which point you're not in real time anymore because you compute for one time step and you only know it the following step. Now, one last thing that I'd like to go over is, before starting the fun stuff, is why we go for FPGA rather than going through CPU most of the time when we want to go for higher simulation time step. So if we go for like a small pseudocode for a CPU within sequential way, so you have two vector, so you initialize and you want to make a dot product. So you want to multiply A time from vector 1 and vector 2, you multiply A time A plus B time B plus C time C and so on. So you can do this, so you have a for loop where you're going to multiply the value and sum them up. If we would like to do this in FPGA, we would use a parallel approach. So you would have all the different value from the different vector that would be multiplied. So after one step or a certain amount of time, the result would be available at the output of each multiplier. Then you can sum them up. And then one more step and you could have the result. So the main idea behind this is that we can now use sequential computation. So at T1, we have those different values at the input of the dot product. Then at T2, we can add new input at the input of the multiplier, but you also have new output available at the output of the summation here, and so on. So after 1, 2, 3 steps, you have the result for the first value you input. But after after 4 steps, you have the value for the second vector, and after 3 steps, and so on. So it takes 3 steps to get the first value, but afterward, it's only take 1 step to get one more value. So you can think of it about like an assembly line. So it takes maybe 1 day to build the car, but you have a car coming out every second. And then once you have one assembly line that works well on the FPGA, you can just put many in parallel to increase the computation power. So this is how, and the main reason why we achieve such a small time step in FPGA is, although that the clock of the FPGA is much slower than the clock of a CPU, everything that is designed on FPGA is specially designed to make extremely efficient for the purpose of or for the thing that you want to do. Now, when we talk about the high switching frequency, the challenging in converter topologies, these come mainly from the high switching frequency of the converter, the fact that those converter has very small time constant, and then at one point you can have a very large number of components for those converter. So those are what makes the simulation difficult. So let's just start with a very simple example of a boost converter. I take the boost converter because everybody knows what to expect from this device. So if we look for the single phase boost converter, and then after that we'll go for the interleaved boost converter. So if we generate a 250 kilohertz PWM, this is the expected result that we're having. Now, if the same converter is sampled in a simulation running at 400 nanosecond, that is actually the signal that is sent to the model. And when you look, you see that there is a small phase shift between the actual signal that you should get and the one that you are actually getting. But you say, okay, it's not so bad. It's pretty close to what would be expecting. But now keep in mind that at 400 nanosecond and at 250 kilohertz, you are on we have a common ratio in between them. So if you just change a little bit the switching frequency, then you can see now that sometimes you're right on it and sometimes you're not right on it, and so on. And this is when you change the carrier frequency. If you vary the duty, you can also have something very similar that happens. So those are things to consider. Now, what we do now is that we're going to do some interpolation between two time steps in order to see what should be the duty that would be applied during that current time step. So at this point here, there's no duty applied, so it's 0. At this time, it's going to be 100%, so we're going to apply 1. But in between, so during this time step where there's going to be a transition, we're going to be applying only maybe 25% or 0.25 to the simulation. The same can apply for an interleave converters. So in that case, you can see that we're going to go for a much lower frequency, but the important thing is the phase shift between this leg and this leg. So even though this can be very good here, then you're going to notice that when considering all of the different legs, you're always going to have a little small phase shift, and this can generate some aliasing in your results. So let's have a closer look to the interpolation. So like I already explained, the idea is that whenever there's a transition that occurs exactly and it's synchronized with the expected PWM, then we won't have any interpolation. It's going to be the right signal, like in the case here. But if the transition occurs towards the end, then we're going to have a smaller fraction. If it occurs at the beginning of that step, then there's going to be a different transition. And using those values in our simulator, we're able to have a very high accuracy on this simulation. Now we're going to go for a very small demonstration to show you a bit what we're talking about. So if we look at the model, so I'm not sure how well you can see it. So this is an interleave boost. So we put 10 phase, 10 leg that are all phase shifted by 10 degree. And so we have a 50 micro Henry inductance and I think 10 micro Farad capacitance. The idea is might not be very realistic, but it's really to show you how the model would behave. So the model is already running. So this is the result that we're getting. So in red, you can see the result that we're having without any interpolation, and in blue are the one that we have when doing the interpolation. And this is for a rather low frequency of it's 1.25 kilohertz. Now, if we just increase to 12 kilohertz, you can already see that there is some aliasing on the red one. So the fact that this one, there's a little wave going like this, it shows the impact of having not the right discretization. And if you look at one single phase current, you can see that the result is not, yeah, maybe I should have explained to you first the different signal. So first here we have the current from one leg. Here we have the DC current, so the sum of all the leg on the DC side, and then we have the DC voltage. So the aliasing that we were seeing and the oscillation that we were observing was on the DC bus, so on the DC voltage. And what I would like to point out is that the error on the current is hardly noticeable. Now, if we look for all the different leg and all of the different currents, so all of those currents are the one that we obtain when we're doing the interpolation, we can see that there is the phase shift between each leg. If we go and decide to just have a quick look, so the frequency that we get is like around 120 kilohertz, because we have a phase shift of since we have 10 times the same signal and it's an interleave boost, so we get 10 times the switching frequency. And this can go on. And now if we want to try to even push harder, let's go for one single phase to be at around 100 kilohertz. Now you can see that the signal is still pretty good. Now, the one thing that we can see is that we are a bit undersampled because this scope is now running at 300 nanosecond. So this is why there's a bit of aliasing. And if we just go using the tool here, then we can observe that we are at about 120 kilohertz for one leg. And if we look at the phase shift between two consecutive leg, we should be around 1.2 so around 1 megahertz of switching between two legs. And if we have a look at the result, so this is the result that we still get with the interpolation, and that's the result that we would get without any interpolation. So depending of what you want to study, you can say that you have like 5 volt oscillation over 220 volts, so it might not be that bad and can be good enough depending of what you're interested in. But what you have to be careful is that if your controller tries to compensate those oscillations while it's running, it might generate even more error. So that's about it for the demonstration. So I see that there's a lot of question coming out, but maybe we can go through the question afterward and we can return to the
we can go to them at the end. Exactly.
Yeah. And we'll return at the same time for the demo. Now another topology that we can consider is the dual active bridge. So in this case, you have this leg and this leg that are controlled, and you only the way it control is usually have 50% duty cycle here, and then you have a small phase shift with this one, and then this is how you determine the power exchange. So if we go for 300 kilohertz at 250 nanosecond, we're gonna get a lousy precision of 27 degree. So with that type of precision, wouldn't be enough to do any control. So this is without any interpolation. Now, if we do some interpolation, if we want to see to have around 1% or 3 degree, so 1% of precision or 3 degree of bandwidth, then we would have something around 40 kilohertz, which is quite low for a 250 nanosecond. So this is why interpolation can become interesting. So nowadays we interpolate our signals on the simulator. So the digital in are simple at 625 picosecond. So we would actually get to have the same 3.4 degree of precision. We could go up to 16 megahertz, but naturally that's not a switching frequency that we're going to go for. So because we have to keep in mind that no matter what the sampling frequencies we're doing, we're still going to be generating a signal from there, and then you still have to get the whole dynamic of the circuit. So let's be conservative and go for a 200 kilohertz. So at this rate of sampling, we would have a 0.045 degree of precision, which is quite accurate. Now, if we look at the signal that we would get, so we try to get a ratio of 15 to 25 times slower than the time step. So at a time step of 250 nanosecond and at 200 kilohertz, we would have a ratio of 20 between the time step and the frequency of the signal that we want to observe. So that's the signal that would be observed in the simulation. And when we look at the harmonic content, so you have the fundamental here, and then at the first harmonic, and then at the 20th harmonic, which is the ratio between the main frequency and the sampling frequency, you're gonna have two dominant harmonic that's gonna be there. That's gonna be one harmonic lower, so at 19 and 21, and so on. So those harmonic are so high that they shouldn't affect much the simulation. Now, if we go for an NLC topology where it's going to be resonating, and the big difficulty in this case is that the whole converter is controlled by frequency rather than by just applying a duty cycle, and you have the diode that's going to need to be rectifying naturally. So if you don't have a very high accuracy on the diode, then you won't get any accurate results. So if we look at the 200 kilohertz that we were applying before, that is actually the signal, the current that we're going to get on the DC side. So the first thing that you have to notice is that the frequency just doubled since we have a dual rectify. Since we're rectifying, now the frequency just doubled. And if you look at the harmonic content, so you have the first harmonic here, but you also have a lot of harmonic that are not neglectable at the second harmonic, third, fourth, and up to the fifth harmonic, I think has to be taken into account. And this is due that is not anymore a nice sine wave, but it's a more complex signal. And this is when you're actually sending power. If you start to go in discontinuous mode, then the harmonic content get even higher, and this signal become even harder to simulate. So this is something that you have to keep in mind when you do the simulation. In order to achieve those signals, you need to go to a much lower frequency. So because now the signal that you're actually observing is going to be 400 kilohertz. So that's why you need to go, in order to simulate switching frequency, around 200 kilohertz, and you want to have all the harmonic content of the rectified signal. You should go more for a time step that is closer to the hundreds of nanoseconds rather than 200 nanoseconds. And finally, to make it things more complex, I haven't seen this converter much, but I'm just figuring out that that's probably going to be the next topology that people's going to want to simulate. So now you have three phase. So the thing is, once you start rectifying, it's not just 2 times the switching frequency that you were applying, but it's 6 times. So from a 200 kilohertz, you go to 1.2 megahertz. So at this point, to do a 3-phase circuit, you wouldn't be able to do it at 200 kilohertz because those frequencies are much too higher to be achieved. And maybe the only thing that I could see that it's positive in this topology is that if you go for the 3-phase rectifying and then you go for higher level, like lower power transfer, even during the discontinuous mode, since there's a 3-phase rectifier, it won't have as little, so the harmonic content won't be that much different. So if you can achieve the accurate simulation when you are at full power, even if you are at very low power, you don't have much more difficulty to simulate it. And so that was everything in a nutshell. So that's pretty much all that we find out about simulation of high switching frequency. So that conclude how much? I always speak too fast, so I don't know what time is it now. Okay, yeah. So we did it just under 22 minutes. So if there's question, well, there is question, and maybe
I can listen to the questions, Vic. I mean, first of all, thank you very much for going quite in detail. I think the audience for sure appreciated seeing all the challenges and things that you overcame. Maybe just as a little context, so everything that you just saw was based on our EHS tool. So for those of you who don't know OPAL or aren't familiar with our tools, we have a software platform called EHS. And if you want to find more, obviously you can go on our website and you'll see a little bit more about it. And with EHS, we're able to sort of take these circuits and create them with our circuit editor that you're seeing right here on the screen. And then we deploy that directly on the FPGA of our hardware. So in other words, you're going from this circuit editor, which you see right here, where you can assign your IOs, all of your parameter sets, and then you deploy it on the FPGA without any reprogramming of the FPGA. So just in a few seconds, you can be in real time. I just wanted to kind of highlight that that's the tool that Luc was using. We did have a question about the plotting tool. So maybe, Luc, if you want to just go over ScopeView a little bit. ScopeView is another tool from OPAL that we use to actually extract and basically plot all of the waveforms that we see in the FPGA. So maybe, Luc, if you want to just give a little bit more of an explanation about it. That's kind of what we're seeing right here.
Yeah, so basically this tool is directly connected to the simulator, and then we in this particular case we are receiving data from the FPGA. So there's a big buffer on the FPGA where we save all the data, and now we're asking for a sampling of 1 microsecond. So those are the signal that we see every microsecond, and then you can zoom in. There are some so for the signal acquisition, here it is. So you can choose the signal that you'd like to plot. Let's say that we want to add a signal here and here. Then you can see that it's add the signal automatically. You have some zoom in and zoom out options. There's some function for also harmonic content. So if you want to calculate the FFT or if you want to have other functions, so you have a bunch of function that comes in so that you can have let's say so harmonic module or so yeah. So this is and it works with most of our simulation tool, and it's allow you to have the acquisition in real time. And I don't know.
Yeah, okay, that's good. On that topic, we had another question, maybe a little bit more introductory. So there was somebody who was asking, what is aliasing? So maybe just in like a 30-second, could you maybe just quickly explain aliasing?
Yeah, so let's say that we go for, well, we can show, I'm just gonna put, let's say, one sample here. So to explain aliasing, so let's say that we do the sampling at every 10 microsecond. So you can see and let's just look at the red signal. So you can see that this signal is like this. So if we look at the frequency that we would have between two harmonic, something like that would be around 5 kilohertz. And aliasing, it's basically meaning that you don't have enough sample to properly represent the signal. So if we go to the full like bandwidth that we can achieve like this, okay. Now you can see that there is it's still 5 kilohertz, but now you can see that there is more oscillation all over the signal. And so basically aliasing is a fancy way to say that you don't have all the information to properly represent the signal in the simulation or in the control. I don't know if it answers.
Okay, and that's good. And I mean, if ever the question wasn't fully answered, feel free to reach out to our support team or to our sales contacts, and we can always go more in detail about that. So no issue there. We have another question. This is a long one. The first question is, what is the typical switching frequency used in EV applications? Maybe I can answer that one just very quickly. It varies, right? So depending who you talk with, and also we can't share all the information of the customers we work with. Let's just say that it varies. But it can be anywhere from basically that our tool supports. So let's say from a few kilohertz all the way to hundreds of kilohertz. That's sort of the range that we see today for those applications. The second part of that question was, how are power electronics switches modeled in those converters? So maybe Luc, you want to just explain quickly about how our solver does it?
Yeah, so in our case, we use ideal switches. So it's they're not modeled, and so you don't have the dynamic of the switching dynamic, and it's more towards having it's going to be a variable resistance, and based on the duty that is applied, then the value of the resistance is going to change. So when it's conducting, it's going to be just the R on. So usually, typically, it's going to be 1 milli ohm, and when it's blocking, it's going to be 100 of kilo ohm, meaning that the circuit is open. And then during during the interpolation, what we're going to do is we're going to apply a ratio of those resistance in order to simulate the right dynamic.
Okay, and then on the last part of that question was related to the switching losses. So I believe in this example, we don't really show the switching losses.
In this, so for the switching losses, it's quite complex, and it's more towards the PWM frequency and the current that is present in the circuit. So for now, since this is the latest module that we made, we don't support switching losses for frequency that high. So our switching module, switching losses module works pretty good up to 50 kilohertz, and this is using the version like what we call the older version, but is the present version of EHS. So I think this has been available for the past 2 years now, and it's a standard product. So the way it works is that you usually give the different parameters of your switch, so all the losses based on the voltage of the switch and the current of the switch, and depending of your switching frequency and all that is applied is going to compute the losses that should be expected.
Cool, thank you. We have another one. I mean, keep the questions coming. And like I said, if ever we don't get through it this presentation, we'll follow up with an email. There was another question from a avid OPAL user. They said, how is the interpolation in EHS different from the interpolation on the CPU? So I believe they're referring to, let's say, the TSB that we use, let's say, with other tools.
Yeah, so the implementation of the TSB is done differently, but the interpolation is basically the same idea. But in some of the issue that we faced earlier back in like I guess was 2010 with the TSB that we had on CPU was that when it's come to blocking, it's hard to have a very good blocking, and then you always have to send gating signal, and we didn't have any diode. Now those issue have been solved, and we kind of implement a very similar way on the CPU and on the FPGA. But the main difference is going to be the frequency that you can reach. Usually on FPGA, it's going to be under 50 kilohertz. Otherwise, you won't have enough point, and you're going to have aliasing again. And on EHS right now, we can go, depending on the topology, we can go 200 or 300 kilohertz.
Okay. I know we're over time. I'll just go with maybe two last questions we have. There's one question related to not necessarily the frequency that we see with our users, but in terms of the tool itself of EHS, do we have an approximate range of sort of the switching frequencies that we can support on the circuit?
Yeah, so right now, like I said, it's going to be depending of the harmonic content that you're willing to observe. Usually, right now, for a small circuit, we're going to get the time step somewhere around 100 to 125 nanosecond. And at this sampling rate, you can go somewhere close to 350 kilohertz. 300, okay. Sorry, 300 to 350 kilohertz. And but then if you want to, you could go higher, but then you have to expect that you might have some error during high impedance, or if you want to go for a three-phase circuit, then you have to consider it to be a bit lower as well.
Okay. And then the last question, I guess, for today, as I know we're over time, is it possible to connect real power, let's say, to the simulation, so that you can have some sort of real power flow between the simulation and the device under test?
Yes. Now, we have to be careful with those switching rate, because usually when we do what we call P-HIL, is that we're going to have decoupling between the simulated model and the real life, whatever that you want to connect. So if you want to inject power from real life, then you have to find something for coupling. And the problem is that usually when we go for a high frequency like that, we don't have a very big time constant in the component of the circuit. So the coupling can become challenging, but we usually find a way to make it work. But so yeah, so if you want to connect yours, if let's say that you're designing an active filter to connect to a network, that shouldn't be any problem. If you want to connect a fast charger to a real battery, and you want to have the whole dynamic of the battery in real life, like I said, it's going to be depending of what's the coupling between the simulated model and the real hardware.
Okay. Okay. Well, thanks, Luc. Again, thank you so much for going in detail with everything that you've done in the past few years with you and your team. And thank you, everyone, for connecting today. We hope that you enjoyed it. Feel free to go on our website, opal-rt.com, to find out more. And if ever you want to learn more, talk to our support team or our sales contacts. We'd love to continue discussing with you guys. So have a nice day, everyone. Thank you.